I want to tell you about the thing that everybody gets wrong about gravity. And I mean, everybody. Your physics teacher got it wrong. Your textbooks got it wrong. For 300 years, the greatest minds in science got it wrong. And here's the embarrassing part, I got it wrong too, for years. You think you know what gravity is, don't you? A force, an invisible pull. Something that reaches out across empty space and tugs on things. Newton said so. Your intuition confirms it. When you drop your keys, you feel them being pulled down. But let me tell you something that still gives me chills when I think about it. Gravity isn't pulling you down right now. Nothing is pulling you at all. Once you understand why, once you really see it the way I finally saw it, you'll never look at the ground beneath your feet the same way. Let me take you back to where this started for me. When I was a young man, maybe 11, 12 years old, growing up in far Rockaway, my father used to take me on walks. And on these walks, he would ask me questions. Not the way teachers ask questions, expecting a specific answer. He would ask me questions that had no answer, or at least no easy answer. One day, we saw a ball sitting in a wagon, and my father asked me, why does the ball roll to the back of the wagon when you pull the wagon forward? And I said, confidently, that's because of inertia! And my father smiled and said, that's Ev name. But what is it? Why does it happen? That question, why does it happen? That became the question that would haunt me my entire life. Because in physics, we get so comfortable with Ev's names that we forget we haven't actually explained anything. And gravity is the biggest example of this problem. For 300 years after Isaac Newton, everyone thought we understood gravity. Newton gave us an equation, a beautiful, a powerful equation. It tells you that any two masses in the universe attract each other with a force proportional to the product of their masses, and inversely proportional to the square of the distance. F equals g times m over r squared. And this equation works. It works magnificently. We can predict the motion of planets, the orbits of moons, the trajectories of rockets. Engineers used Newton's equations to send men to the moon. To this day, NASA uses Newton's equations for most of their calculations. So what's wrong with it? Newton himself knew something was wrong. He was deeply troubled by his own theory, and he said so. He wrote that the idea of objects acting on each other across empty space instantaneously, with nothing between them, was so great an absurdity that I believe no man who is competent thinking in philosophical matters can ever fall into. Newton didn't believe his own theory, at least not completely. Think about what Newton's gravity requires you to believe. The sun is 93 million miles away, and somehow, right now it is reaching across that vast emptiness and pulling on the earth. No wires, no ropes, nothing but empty space, and yet somehow the sun knows the earth is here and is exerting a force on it. How? How does the sun know where the earth is? How does the force travel across that space? And if the sun suddenly disappeared, poof, just vanished, would the earth immediately fly off in a straight line, or would it take some time for the news of the sun's disappearance to reach us? Newton had no answer. He could tell you how much the force was. He couldn't tell you what the force was or how it worked. And this is where I started to get interested. Because I don't like magic. I don't like explanations that say, this thing happens because of this, and when you ask what this actually is, everyone shrugs and changes the subject. When I was teaching at Caltech, and I'm talking now about the 60s and 70s, students would come to me and say, Professor Feynman, I don't understand gravity. And I would say, good, neither do I. They thought I was joking. I wasn't joking, because Newton's gravity isn't an explanation. It's a description. It tells you what happens. It doesn't tell you why it happens or how it happens. It's like saying, why did the ball roll to the back of the wagon? Because of our rollingness. You haven't explained anything. You've just given the mystery a name. And then along came a man who actually did explain it, Albert Einstein. And what he discovered was so strange, so alien to our everyday experience, that most people still don't really understand it, even if they think they do. The key to understanding gravity, the first real key, starts with a question that seems almost stupid. It's so simple. Why do all objects fall at the same rate? This goes back to Galileo. Legend has it he dropped 2 balls of different weights from the Tower of Pisa, and they hit the ground at the same time. Whether he actually did this or not, the fact is true. A hammer and a feather, if you remove the air resistance, will fall at exactly the same rate. Now, if gravity is a force that pulls on objects based on their mass, heavier objects get pulled harder. Then why don't heavy objects fall faster? The usual answer is because heavier objects are also harder to accelerate. They have more inertia. These two effects exactly cancel out, and that answer is ours correct. But let me tell you why that answer never satisfies us. What a coincidence. The force of gravity on an object is exactly proportional to the very same property, mass, that determines how hard the object is to accelerate. These are two completely different concepts. Why should they be equal? Why should gravitational mass and inertial mass be exactly the same thing, down to the last decimal place we can measure? It's as if you discovered that the electrical charge on every particle in the universe was exactly equal to its weight in grams. You would say, wait a minute. That can't be a coincidence. There must be something connecting these two things. And Einstein said, you're right. It's not a coincidence. Let me tell you about the thought experiment that changed everything. Einstein called it the happiest thought of my life. Imagine you're in an elevator, no windows. You can't see outside, and you're floating, weightless, like an astronaut. Now, there are 2 possible explanations for why you're floating. Possibility 1. The elevator is floating in deep space, far from any planet or star. There's no gravity, so you float. Possibility 2. The elevator is near Earth, but it's falling. The elevator is in free fall, plummeting toward the ground, and you're falling with it. Inside the elevator, you feel weightless. Here's Einstein's question. How would you tell the difference? And the answer that changed physics, you can't. There is no experiment you can perform inside that elevator that will tell you whether you're floating in empty space or falling in a gravitational field. None. Not with any instrument, not with any measurement. It's not that we don't have good enough equipment. It's that the 2 situations are physically identical. Now turn it around. Imagine you're standing on the floor of an elevator, feeling your normal weight, your feet pressing down. Gravity, you think. But again, 2 possibilities. Possibility 1, you're on Earth, and gravity is pulling you down. Possibility 2, you're in deep space, far from any planet, but the elevator is accelerating upward. Some rocket is pushing the elevator up at 8 meters per second squared. And again, how would you tell the difference? You can't. Einstein called this equivalence principle. Gravity and acceleration are equivalent. They feel identical because they are identical. And this is where I began to see what Einstein was really saying. He wasn't just making a clever observation. He was telling us that gravity isn't a force at all. Now, I have to be careful here, because what I'm about to explain is one of the most misrepresented ideas in all of physics. You've probably seen the picture. A rubber sheet with a bowling ball on it, creating a dent, and the marble rolling around the dent. That's how they explain curved space-time in almost every documentary, every textbook, every popular science article. And that picture is wrong, or at least it's so incomplete that it misleads more than it helps. Because why? The rubber sheet analogy suggests that space is curved. Objects roll downhill into the dip. But wait, what's making them roll downhill? Gravity. So you're using gravity to explain gravity. You haven't explained anything! This bothered me for a long time, and it should bother you too. The real picture is stranger and more beautiful, and it took me years to really understand it properly. Here's what Einstein actually said. Mass and energy don't just bend space, they bend time, and it's the bending of time that creates what we call gravity. Now, I know this sounds bizarre. How can time be bent? Time is just time, right? A second is a second. No, a second is not a second, not when gravity is involved. Here's something that has been measured, not theorized, measured. A clock at the top of a tall building runs faster than a clock at the bottom, not by much. A few billionths of a second per year. But it's real. GPS satellites have to account for this, or your navigation would be off by miles. Time runs slower where gravity is stronger. The closer you are to a massive object, the slower your clock ticks compared to someone far away. And this difference in the flow of time is what creates the effect we call gravity. But wait, how does slow running time make you fall? This is the part that took me the longest to understand. And when I finally got it, I had one of those moments. You know, those moments where the world suddenly looks different, where you realize you've been seeing things wrong your whole life. Let me explain it this way. Right now, you're sitting there. Maybe you think you're not moving, but you are moving. You're moving through time. Every second, you move 1 second into the future. You can't help it. You can't stop it. You are always moving through time. Now, in Einstein's picture, space and time are not separate things. They're woven together into spacetime. 4 dimensions, 3 of space, 1 of time. And here's the key insight. Everything moves through spacetime at the same speed, the speed of light. But here's the trick. You can divvy up that motion between space and time. If you're sitting still, all of your motion through spacetime is going into the time direction. You're moving through time at maximum speed. If you start moving through space, if you get in a rocket and fly somewhere, some of your motion gets diverted from time into space, and your clock slows down. This is time dilation, which we've measured. Now, what happens when spacetime is curved? Imagine you're standing on Earth. Your head is slightly farther from Earth's center than your feet. Time runs slightly faster at your head and at your feet. Your head wants to move through time faster than your feet. But your head and your feet are connected. They're part of the same body. They have to move together through space-time. And when you work out the geometry, then you ask, what path keeps the body together while respecting the different rates of time? The answer is, the body accelerates toward the ground, not because anything is pushing it, not because any force is pulling it, but because that's the straightest possible path through curved space-time. You're not being pulled down by gravity. You're following the straightest line through a curved geometry. Now, here's what changed everything for me. Let me tell you about the astronauts. Astronauts in the space station are floating, weightless. We call it zero gravity. But wait, the space station is only about 250 miles above Earth. The gravitational force up there is about 90% as strong as on the surface. They're off not escaping gravity. Gravity is almost as strong there as here. So why are they floating? Because they're falling. The space station is falling toward Earth. It just keeps missing. Its sideways motion carries it past the edge as it falls, so it falls around and around in a circle, an orbit. Inside the station, everything is falling together. The astronaut and the spacecraft and the coffee cup all falling at the same rate. Relative to each other, nothing moves. It feels like weightlessness. But here's the profound part. The astronauts in free fall are not feeling gravity. They're following the straightest possible path through spacetime, what we call a geodesic. And when you're on a geodesic, you feel nothing, no force, no push, no pull. Free fall is the natural state. Now think about yourself sitting in your chair. You're the one being pushed. The chair is accelerating you upward, away from Earth, at 8 meters per second squared. The chair is preventing you from following your natural path through curved spacetime. And that resistance, that push of the chair against your body, is what you feel as weight. You're not being pulled down by gravity. You're being pushed up by the chair. I remember when this finally clicked for me. I was working through the equations of general relativity, and I should tell you, these equations are hard. They took Einstein 10 years to work out, and they took me a long time to really understand. And I was sitting in my office at Caltech, and I felt the chair pushing against me, and I suddenly thought, this is wrong. The chair is the thing that's accelerating me, not gravity. The chair, and I looked at the floor, and I imagined the floor falling away, and I realized the floor is what's creating the force. The floor is ever accelerating toward me at 8 meters per second squared. But wait, the floor isn't moving, right? How can it be accelerating? And this is where spacetime curvature comes in. Near a massive object like Earth, spacetime is curved. And in curved spacetime, even objects that are sitting still relative to each other can be accelerated, not through space, but that through spacetime. The floor is being pushed upward by the ground beneath it, which is being pushed by the layers below, all the way down to the center of Earth, where the pressure holds everything. That whole structure is accelerating relative to free falling spacetime. You, sitting on your chair, are part of that structure. You're being accelerated, and what you feel as weight is the sensation of that acceleration. Meanwhile, a falling apple is not accelerating. The apple is following its natural path, its geodesy, through curved spacetime. From the apple's perspective, it's weight. It's a piece. It's doing what objects naturally do when nothing messes with it. We are the ones under constant assault from the floor. This is the complete reversal of everyday intuition. You think the apple is being pulled down by the force of gravity. But there is no force on the apple. The apple is in the most force-free state possible. You are the one being acted on by a force, the electromagnetic force of the atoms in your chair resisting compression. Gravity isn't a force pulling things down. It's a distortion of space-time, and objects in free fall are simply following straight lines through that distortion. And here's something else I realized. Newton's gravity was action at a distance. Somehow, the sun reaches across 93 million miles of nothing and tugs on Earth. That's strange. That's almost supernatural. But in Einstein's picture, there's no action at a distance. The sun curves the space-time around it. That curvature extends outward. And Earth, 93 million miles away, is simply responding to the curvature right where Earth is. The sun doesn't have to know where Earth is. The sun curves space-time. Space-time tells Earth how to move. Matter tells space-time how to curve. Space-time tells matter how to move. Everything is local. No magic. No action at a distance. Now I want to tell you about the predictions. Because a theory is only as good as its predictions. Newton's gravity predicts almost everything we see. But Einstein's gravity predicts more. It predicts things Newton couldn't dream of. Let me give you an example. Mercury, the innermost planet. Mercury's orbit isn't a perfect ellipse. Each time Mercury goes around the sun, the ellipse rotates slightly. The point closest to the sun shifts. This is called precession. Newton's equations predict most of this precession. It's caused by the gravitational pull of other planets, mainly Venus and Jupiter. But when astronomers carefully measured Mercury's precession, they found a tiny discrepancy, about 43 arc-seconds per century, a tiny, tiny amount, but real. For decades, astronomers couldn't explain it. They even proposed a hidden planet, Vulcan, between Mercury and the Sun, causing the extra precession. They searched for it, never found it. Einstein, using general relativity, calculated the precession of Mercury's orbit in 1915. He got exactly 43 arc-seconds per century. The extra precession comes from the curvature of space-time near the Sun. Newton's flat space approximation misses it. Einstein's curved space-time captures it perfectly. He later wrote that when he saw the calculation work out, his heart literally pounded. But that's not all. Einstein predicted that light itself would be bent by gravity. Not because light has mass, photons are massless, but because light follows geodesics through curved spacetime, just like everything else. In 1919, during a solar eclipse, Arthur Eddington measured the positions of stars near the Sun. Their light passing close to the Sun on its way to Earth was a bend, exactly as Einstein predicted. The next day, Einstein was famous. Headlines around the world: light bent by gravity, Newton overthrown, and then there's the bending of time itself. I mentioned this earlier. Clocks run slower in stronger gravitational fields. This isn't just a curious fact. It has practical consequences. Every GPS satellite in orbit carries atomic clocks. These clocks are farther from Earth, where gravity is weaker, so they run faster than clocks on the ground. About 45 microseconds per day faster. At the same time, the satellites are moving relative to Earth, which causes time dilation. Their clocks run slower due to their velocity, about 7 microseconds per day slower. The net effect: GPS satellite clocks gain about 38 microseconds per day relative to ground clocks. If you didn't correct for this, GPS positions would be off by kilometers within a day. Your phone would tell you you're in the middle of a lake. General relativity isn't some abstract theory. It's built into the navigation system in your pocket. And then there's the most spectacular prediction of all. If mass curves space-time, what happens when masses move? When two massive objects, like two black holes, spiral into each other. Einstein predicted that moving masses would create ripples in space-time. Waves, propagating outward at the speed of light. Space-time itself would stretch and squeeze as these waves passed through. He predicted this in 1916, but the effect is so incredibly tiny that he wasn't sure it could ever be detected. For 100 years we couldn't detect it. And then, in 2015, nearly a century after Einstein's prediction, the LIGO detectors picked up a signal. Two black holes, about 30 times the mass of the Sun each, spiraling into each other over 1 billion light years away. As they merged, they released more energy than all the stars in the observable universe, but released it as gravitational waves. By the time those waves reached Earth, they were so faint that they stretched and squeezed LIGO's 4-kilometer-long detectors by less than 1,000th the diameter of a proton, and we detected them. When I heard about this, and of course, I wasn't around to see it myself, but I'm speaking to you now from a perspective where I can reflect on all of physics. I thought, this is vindication. This is nature telling us that Einstein was right. Space-time is areal, curved, it ripples. It does all the strange things the equations say it does. And gravity was never a force at all. And then it hit me. Let me tell you what I finally understood, and why it still takes my breath away. When you drop an apple, it falls to the ground. Here's what's actually happening. The apple is following the straightest possible path through space-time. It's not accelerating. It's not being pushed or pulled. It's in the most natural, most force-free state possible. Weightless. Peace. You, standing on the ground, you're being pushed. The electromagnetic forces between atoms in the ground are pushing up on your feet, preventing you from following your natural geodesics. You are being accelerated upward at 8 meters per second squared, constantly, relentlessly. And here's the crazy part. From the apple's perspective, if the apple could have a perspective, you are accelerating toward it. The ground is rushing up to hit the apple. The apple is just minding its own business, floating peacefully through curved space-time. You are the one doing something weird. This is the complete inversion of everything you thought you knew. There is no force of gravity. There never was. Newton's force was just a useful approximation. a way to predict what would happen without understanding why. What actually exists is curved spacetime, geometry, and objects move through that geometry along the straightest paths available to them. When the geometry is flat, far from any mass, objects move in straight lines at constant speed, inertia, Newton's first law. When the geometry is curved near a massive object, the straightest paths bend. Objects appear to accelerate toward the massive object, but they're not being pushed or pulled. They're just following the geometry, and the thing we call weight, that sensation of heaviness, of being pulled down, that's not gravity. That's the floor. That's the atoms in the ground, pushing back against you, accelerating you away from your natural path. I'll never forget the moment this clicked. I was walking across campus, and I looked at the grass, and I thought, the ground is accelerating at me. The whole earth is accelerating outward in every direction, at every point on its surface, pushing against everything that tries to fall. Of course, the earth isn't expanding. Its surface is held up by pressure and structure. But relative to the curved spacetime around it, relative to the geodesics that free falling objects follow, the surface is accelerating outward. And I looked up at the sky, and I thought about satellites, astronauts, comets, planets, all of them in free fall, all of them weightless, all of them following geodesics, doing what nature intended. And I realized, we are the ones being pushed. We are the ones under constant assault from the ground. We are the ones experiencing a force. Falling objects are at peace. We are not. This changed how I see reality. Because here's what it means: the universe is not a stage on which events happen. The universe is the events. Space and time are not background. They are active. They curve. They ripple. They respond to everything in them. And gravity, this thing we named, this thing Newton called a force, it's not separate from space-time. It is space-time. The curvature is the gravity. There's a beauty in this. An element. Newton gave us a recipe. Einstein gave us a understanding. Newton told us what happens. Einstein told us why. What's this why? This why is geometry. Ey is that massive objects curve the fabric of reality. When everything moves through that curved fabric along the straightest lines available. The why is that there is no force called gravity. There never was. Just the geometry of the universe, bending and flexing. And us, along with everything else, moving through it. I tell my students, don't be satisfied with names. Gravity is a name. Space-time curvature is also a name. What you want is the picture, this understanding. You want to be able to close your eyes and see what's happening. And here's what I want you to see. Right now, space-time is curved around you. The earth is warping the fabric of reality, and your body wants to follow a geodesic, a path curving toward the center of the earth. But your chair is pushing you, accelerating you upward, preventing you from falling. You feel that push as weight. But it's not gravity pulling you down. It's the chair pushing you up. Free fall is freedom. Weight is resistance. I find this beautiful. Not just because the equations work, though they do, spectacularly, but because it shows us something about the nature of reality that we couldn't have guessed. It reveals a hidden structure, a secret geometry underlying everything we see, and it tells us that our intuitions, our everyday sense that gravity is a force reaching out and grabbing things, that intuition is as wrong. And reality is stranger and more elegant than we imagined. The apple isn't falling, the apple is at peace. You are being pushed. This is the beauty of physics. And I wanted you to experience it with me.